All right, so today's focus will be on PI, this thing called PI, which is Isoelectric Point, and a little bit about electrophoresis, okay? So pick up from where we left off last week. This is sort of a thing about polyprotic acids, okay? Polyprotic acids essentially means that it's an acid that have multiple pKa, okay? So any polyprotic acids will be a species that have multiple protons that you can remove. Okay, for example, you have amino acids like these. Right? This is the simplest amino acid called glycine. Okay, and for glycine, you have two protons in which you can remove. Okay, when it's fully protonated, you have a proton here, a proton here. Okay. So then the first pKa that you will see, right, is going to be this particular proton, and the pKa for that particular proton is 2.3. Okay? And then as the pH increases, okay, gradually when you get to alkaline enough, like basic enough, then you are able to pull off this proton as well. Okay? And when you pull off this proton, it becomes NH2 instead of NH3+. Okay, so polyprotic acids, essentially it's just a term that we give to acids that have multiple protons that we can remove. Okay, so a different example would be triprotic acids. Okay, so it's also a part of polyprotic acids. That is H3PO4. Okay, so obviously you can see how there are 3 hydrogens there that you can remove as protons. Okay, so each of those protons will have their own pKa. Okay. So isoelectric point, okay, is a particular thing that we like to talk about when we talk about proteins actually, okay? And what it is essentially a point where the molecule becomes neutral, right? So before we get there, there are a couple of terms that we want to define real quick. Ampholyte, okay, that's the first term you got here, ampholyte. Ampholyte is a molecule with both acidic and basic groups, okay? So acidic group essentially is talking about organic acid, okay? And then basic group is talking about this guy right there, okay? So if you look at those two, what do you think? Okay, so we are going to be talking about amino acids. All right, so then isoelectric point, okay? Iso meaning same, electric meaning, charges, okay, electricity. So isoelectric point is the pH, okay, so it's a pH, we're talking about a particular pH at which the average charge, okay, of all forms of the molecule is 0. Okay, so we'll see some examples a little bit later, but for now, just take the sentence and just take my word for it. It basically means that this is the pH in which the charge on the molecule becomes 0, okay? Because the molecule has both acidic group and basic group. So acidic group, if you remove the proton, it becomes a negative charge. So you can go between neutral and negative, okay, for acidic group. Basic group, okay, the basic group, you can go from neutral and positive charge. Okay, so if you have acidic group, it will make your molecule become negative charge. If you have basic group, it will make it positive charge. So ampholytes have both. So there's going to be a pH in which they're going to be balanced. Okay, so then that is what we call PI. Now, at pH, okay, so if the pH, the current pH is lower than the PI, right? Then the molecule will be positively charged. Why? Because if it's lower than the PI, protons will be on the molecule more. Okay? So when the pH is lower than the PI, then that just tells you that your protons in the solution is going to end up on your molecule. So the acidic portion, okay, the acidic group of the molecule becomes neutral. Okay, so this guy becomes this guy, right? So this guy is now neutral. Okay, so at low pH, right? So at low pH, of course, this becomes that. Okay, so it's going to be, this is going to be positive charge. Right? As a result, your molecule will be positively charged. Okay, that's just how it is. Okay, it's because your acids are getting protonated to become neutral, whereas your amino groups, the basic group, is going to get protonated and it becomes positively charged. All right? So the reverse is true about if the pH is larger than your pi. Okay, so if the pH is larger than the pi, that means that the proton is going to move away from the molecule and going to end up in the solution. So if you're removing proton from the solution, you make negative charge and neutral. Okay? So you can see how when pH is greater than pi, the molecule will become negatively charged. That's great. Okay? So all amino acids are enphalites. Okay? That is just like all amino acids are enphalites because all amino acids have an amino group, which is a basic group. All of them have acid groups, which is acid group, which is a negative charge, right? So amino acids will have amino groups, which is a basic group that will become neutral or positive. And they also have an acid group, carboxylic acid group, that will make them go from neutral to minus. Okay? So all amino acids are enphalites, right? So as a result, so like this amino group can have a positive charge, carboxyl group, okay, or the acid group can have a negative charge. Now, since polypeptides or proteins are made out of amino acids, so all proteins are also in a way enphalites, okay? Because when you have proteins, peptide formation, your amino reacts with a carboxylic acid, okay? But, okay, let's say they react. Still, you have N terminus, which is amino group, and you have a C terminus, which is an acid group. Okay, so proteins are also enphalites. Okay, they have very similar characteristics. Right, so proteins have pi. Okay. Now, amino acids are enphalites. Okay, so molecules with both acidic and basic groups. So what are the acidic and basic groups of amino acids? We just answered that. That's going to be the COO minus for the acidic, and the amino group for the basic. Okay. Yeah. So isoelectric point, like I said, it's the average charge where it becomes 0. So we talked about those two. So at the pH equals to pi point, the molecule will become neutral. Okay. And that just means that it has no net charge. Okay. So they can balance out. It could have a positive and a negative simultaneously, right? But together they balance each other out, and then the molecule becomes neutral. Does not mean the molecule is not charged. Okay? The molecule can still be charged, but overall it is neutral because it has both positive and negative. Right? And this is something special we call the Zwitter ion. This you should know. Okay? This guy you should know. It's a special term, which essentially just says that you have a molecule and you have a negative and positive simultaneously, but overall neutral. Okay? That's essentially what it means. Right? So Zwitter ions are quite useful for biomaterial development. So that's something that you should know. Okay? All right. So the pi of enphalites with two ionizable groups can be determined through simple titration. Okay? What does that mean? Okay, what does that mean? All right. First of all, let's take this amino acid as an example. This is glycine. Again, glycine. Glycine has 2 pKa. 1 pKa is the acid proton, and the other pKa is the protonated amino group proton. Okay, so you got 1 pKa, 2 pKa. Okay, so let's say you get glycine and you glycine, and you get this fully protonated version of it. Okay, and you throw it in water. Okay, and you look at your titration curves. Essentially what that is you dissolve your protonated glycine into your water, okay? And then you start adding OH equivalents. Okay, so let's say you start with 1 molar of protonated glycine, right? And then of course the pH is going to be low because it's protonated, okay? So it's going to make your water more acidic, right? pH is going to be low. You start adding an AOH to it, okay? That's called titration, guys, okay? Titration. And you're titrating, right? And remember our Henderson-Hasselbalch equation of pH is equal to pKa plus log of the A minus over HA. Remember that? Okay? So at the very beginning, you're going to looking at pH and pKa, right? Okay? Now, so you start adding your OH minus, and initially it's going to jump up the pH real quick. Okay? It's going to increase it real quick because you have mostly HA, okay, because it's protonated. And then very quickly you're going to enter essentially the buffer zone, okay? So that like that's the buffer zone. And then gradually the slope change is going to become really slow, nearly 0, okay? So this is the point where you have the first pKa, okay? And then you keep on titrating it with an AOH, okay? Keep on titrating it. Now the pH is going to continue to increase. And then all of a sudden, it's going to go up like crazy and enter another zone of a buffer, okay? So that is the other pKa, okay? So this is what a typical titration curve for a polyprotic acid going to look like, okay? So I don't know if you guys are going to do this in lab, but it's actually a very interesting experiment that you can do. Okay, you get an amino acid from your TA, okay, dissolve in water, you start titrating it, and then you can see the 2 pKa's, and then you can go to your book and say, oh, okay, this is glycine. Okay, not very exciting, but it's a lab that we used to do. Okay, so after you find pKa1 and you find pKa2, okay, somehow PI is going to be in the middle, okay, and I'm going to show you how to calculate PI. Turns out, okay, the PI for an ampholyte that has 2 ionizable groups, essentially it's just the average of the 2 pKa's, okay. I mean it's really dumb, right? But that's just how it is, okay. So if you look at our glycine example, and you will see that the first pKa is 2.3. Second pKa is 9.6, so you add them up, divide by 2, and the PI is going to be 5.97, okay? And that's the pH at which this molecule becomes net 0 charge, okay? Cool? We're good with that? Pretty simple, right? So let's take a detailed look at the individual species in this process, okay? So this is, again, still glycine. This is still glycine, okay? And it's a very simple molecule, has an acidic group, has a basic group, okay? Simple. All right. At the very beginning, you have all right, so on the x-axis, that's the pH, okay? That's the pH. On the y-axis is the fraction of glycine from 0 to 1, okay? 1 being 100%, 0 being 0% of a particular form of glycine, okay? So at the very beginning, when pH is equal to 0, okay, so somehow your pH is equal to 0, you have essentially 100% protonated glycine on both ionizable groups, okay? So it's going to be positive charge 1, right? And as you're starting to add OH minus, and you can see how the species of your glycine starts to change. You go from the protonated, so this guy is a protonated, this guy is neutral, this guy is minus charged. And as you're adding OH minus, okay, you are starting to lose your charge. Okay, so let's say this guy is +1, gradually it's going to be, plus, I don't know, 0.6, blah, blah, blah. And at here, at the first pKa, half of them will be charged, half of them will be neutral, okay? So this point is where half charged, half neutral, okay? Why is that? Because A minus equals HA, okay? And this cancel, pH equals pKa, right? So that essentially tells you that this is equal to 1, log of 1, 0, okay? And in order for them to equal to 1, your A minus has to equal HA, okay? So that's that. And as you're titrating it further using NaOH, gradually you are reducing your positive charge, and then eventually you end up at your zero ion form, okay? And then you keep on adding your OH minus. Gradually you're starting to pull away the proton on the amino group, okay? So you can see how the neutral form is going to decrease in population, and the basic form, or the minus charge form, is going to increase in population. And by by pH of 12, you have pretty much all of your species being the minus charge form, okay, the basic form, the deprotonated form, whichever you like to call it, okay? Does that make sense? I think this chart is quite self-explanatory, okay? It's pretty simple, okay? Now, so in your textbook, in table 2.9, okay, it sort of just tells you a little bit about, you know, what happens when you have a pH equal to pKa, okay? So if pH is equal to pKa, then your A minus, okay, is protonated 50% of the time, right? So what does that mean for your two species? For the COO minus, it's protonated 50% of the time. That gives you a net charge of minus 0.5, right? Because you have half being COOH, which is neutral. You have another half, which is COO minus, which is negative, right? So half and half. So then you have a net charge of minus 0.5. Make sense? Yeah, we're good. All right. So the same logic applies to the amino group, okay? So when the pH is equal to the pKa of your amino hydrogen there, then your amino group is protonated 50% of the time, which then means that the net charge is going to be positive 0.5. Okay, simple, right? So the pH, if your pH is lower than the pKa, that's meaning that your acid is going to be protonated greater than 50% of the time, okay? So the net charge is going to be greater than 0.5 and less than 0. Okay, does that make sense? Okay, so it's going to be minus like 0.3, minus 0.2, right? It's becoming less minus as the pH drops. Okay, so just think of it as simply the lower the pH of your solution, the more protonated your molecule becomes. Okay? So the same logic works when your pH is greater than your pKa. Okay? If the pH is greater than pKa, then the proton on your molecule is starting to leave. It's going to end up in the solution so that your molecule is going to turn more positive. Okay? So that's that. All right. Now, we're going to talk a little bit about amino acids and their pKa's. Okay? Turns out, okay, pKa of a specific proton, of a specific functional group, can be affected by its surrounding environment. So we talked about this, or briefly touched on this thing when we talked about enzyme. You know, I showed you a picture of how enzymes function in terms of like that histidine can move the proton on and off, right? So essentially, your proton is going to feel its environment. Okay? It's going to feel the environment. And this environment could be intramolecular or intermolecular. Okay? The environment could mean on the same molecule or in the environment at which it's surrounded by. Okay? Now, let's take a look at acetic acid. Okay, this is acetic acid you find in your vinegar. Acetic acid can deprotonate, become acetate, and the carboxyl group has a pKa of 4.8. Okay, sure. And you take a look at methylamine. Okay, so just one carbon amino group. Okay, you go from the protonated form to the deprotonated form. The pKa for the protonated amino group is about 10.6. Okay, that's cool. Now, if we look at glycine, okay, glycine amino acid, the amino acid group, okay, this particular acid group, if you want to lose this proton, okay, like this, the pKa for that proton is 2.3. All right, somehow you went from 4.8 to 2.3, but it's the same functional group, right? It's COO minus, it's COO minus, okay? Somehow you go from 4.8 to 2.3, okay? So let's discuss how this happens, right? Turns out, you have repulsion between the amino group and the departing proton. What does that mean? At low pH, this guy is protonated, so it has a positive charge. Okay? COOH, H is partial positive, the O's are partial negative. Okay? So in a way, you have repulsion going on, okay? Because this guy is partial positive, this guy is positive, so you got some kind of repulsion going there, okay? So it's going to push away the proton. That's the first effect, okay? So pushing it away, it wants to push it away, okay? Because you have the protonated amino group right there, you want to push the proton away. So that lowers the pKa, right? Because lower the pKa, the easier it is to take the proton. Okay? That's the first effect. Right? Now, there's a second effect. Right? The second effect is that the oppositely charged groups will actually lower the pKa by stabilizing the zwitter ion. Okay? So essentially what happens is after you form this minus charge, you have a minus, you have a positive, they stabilize each other. Okay? So you want to form this guy. This is stable. Okay? Because you have a positive there, and positive is going to push away your proton. That's the first thing. The second thing is the positive charge can be stabilized by a negative charge on the same molecule. Okay? So the resulting, this thing, is stable. So if this guy is stable, it makes the proton leave easier. Okay? So that's why you go from a pKa of 4.8 on acetic acid to a pKa of 2.3 on glycine. Okay? Now, this you have to explain. For the amino group, okay, on methylamine, the pKa for the protonated amino group is 10.6. This guy is 10.6. But then the pKa for the amino group of the protonated amino acid, okay, is 9.6. So it's lowered. Okay? So it's also lowered. It also becomes easier to pull off. All right? So it turns out the electronegative oxygen atoms in the carboxyl group pull electron away from amino group, and it lowers the pKa. Okay? What does that mean? Okay? Essentially, right? Essentially, by having this negative charge, okay, it's going to draw the electrons towards it. Okay? It's going to draw the electrons from the amino group towards the carboxyl group, such that this whole molecule, you can think of this whole molecule, the electron density is moving towards this portion. As a result, this becomes really positive. Okay? As a result, this proton can be pretty easily or easier to be removed by your base. Okay, now you're going to be asking me, but wait a minute, if it is removed, then doesn't it become less stable? Okay, which is why you don't have as a significant change to the pKa as the acid. You go from 10.6 to 9.6, but here you go from 4.8 to 2.3, right? So the change is more significant for kicking out the acid, not as significant for kicking out the protonated amino group. Does that make sense? Okay, so just read this description and it should help you understand. All right, we're cool? Cool with this? That's important, okay? This is important. It sort of tells you why amino acids have these pKa's, okay? Now, this is a chart of the 20 amino acids. Yeah, so you see the 20 amino acids and you look at the pKa values for the acid group, okay? And you see it's somewhere between 2, 2.4. Some of them could go down to 1.8. Okay, that's fine, right? But roughly speaking, we have something like 2 to 2.2, okay? So that's the pKa for your amino acid group, okay? That's the acid group. Amino group, okay? So it's going to be around like 9 to 10, okay? So roughly 9.6, 9.5. Some of them are really high, like 11. Some of them are really low, like 9, okay? But roughly speaking, 9 to 10, somewhere there. Okay, so you should know that, right? So if I just throw a random question at you and say, okay, at pH of 7, do you think your amino acid is charged? You should be able to answer that question, okay? Now, some amino acids will have R groups, the side chain, that has a ionizable group. For example, you have arginine, aspartic acid, cysteine, glutamate, histidine, and lysine and tyrosine. Okay, so these guys have pKa's for their R group. Okay, of course, some of them are not really relevant to us. For example, 12.5. Yeah, you're not going to pull that off. Okay, 12.5 is pretty high. Hardly you can pull it off. But if you look at 6 is a good number. You can go on and off pretty easily. Okay, this is mostly off. This is mostly off. Okay, this is always on. On and off meaning the protons. Is it on the molecule or is it off the molecule? Okay, so you can sort of think of it that way. All right, so this is pKa for amino acids. All right, we're cool? You guys are good with pKa now, right? So now we're going to talk about pi. All right. So given any polypeptide, the pi is going to be between the pKa's of 2 protons that make the peptide from -1 or +1 to 0. Let me show you what that means. All right. Here is a tetrapeptide. Right, so it's a polypeptide that has 4 amino acid residues. Okay. So first thing you want to do is you want to identify how many ionizable groups are there on this molecule. Okay. You have the N-terminus amino and the C-terminus acid. You always have those two. And in this case, you have alanine, glutamate, glycine, lysine. Glutamate has a R group that has a COOH. It's an acid. Okay? The pKa for this guy is going to be 4.2. Why is it not 2.3? Because it doesn't have the amino right here, right? No amino right here. So the pKa for this guy is going to be quite similar to your acetic acid, right? So you don't have the, the whole pushing effect or the stabilization effect, right? All right, so this guy is 4.2. And you have lysine, and lysine is an amino group. That's pKa of 10. Okay, so you have these 4. All right, so what's the pi going to be? It's not, you add the 4 up, divide by 4. No, okay? It's not that simple. It doesn't work that way, right? Turns out, it's going to be 4.2 and 9.7 divided by 2. I'm going to tell you why. Okay, I'm going to tell you why. All right. So to determine PI or to estimate what the PI will be, what I usually do is I say, okay, when pH is equal to 7, what is the charge on this molecule? Okay, all right, with me so far? pH is 7, this guy is going to be what charge? This guy, the top one. It's going to be protonated or deprotonated. Just tell me that. Protonated, deprotonated, when pH is equal to 7. What do you guys think? So when the pH is lower than the pKa, that means that this molecule is going to get protonated, right? Maybe okay, maybe. We all agree? Anybody say deprotonated? No? Okay. So if it's protonated, that means that the charge is going to be 0 or positive or negative. Positive 1, right? Okay. Let's say this is positive. Okay. How about this guy? Is it going to get protonated or deprotonated at pH 7? Deprotonated, right? So it's going to get deprotonated. Okay. How about this guy? pKa of 10, right? pKa of 10, so pH lower than the PI. That means that the proton is going to go where? It's going to get protonated, maybe. Okay. Protonated. Right? All right. So what about the last one? It's an acid group, right? So it's going to get protonated or deprotonated. Deprotonated, right? Okay. It's going to get deprotonated. All right. So if you just look at this and you say, well, okay, so it's going to be neutral at pH 7. Not quite, okay? Not quite. So usually, after you find a pH that you can draw on the molecule and you say, okay, this is going to be neutral at this particular pH, then you want to take the pKa right above pH, this particular pH, and right below this particular pH. And then you take those two groups, you average them. So let's say I started at pH 7, right? The group that has a pKa right above 7 is which one? You have 4 choices. It's the 9.7, right? Right below, it's the 4.2. Okay? That's why the pKa, the PI for this particular peptide is going to be 4.2 plus 9.7 divided by 2 and gives you about 6.9. Okay, and you're like wondering, did I invent this? Okay, no. Okay, I didn't invent this. Okay, in a way, it makes sense. Why? Why is that? Okay, why is that? So let's say today you identified a pH that makes the molecule look neutral. Okay, it makes the molecule look neutral, right? That means that any group that are really far away from this pH is not going to affect the charge of this particular molecule because it's too far away, right? So let's say you go from, I'll give you another condition. How about we just draw another condition? If it's pH equal to 3, okay, again, this one's positive, this one, still negative, or neutral. When pH is equal to 3, this one is going to be negative or neutral? Neutral, right? Okay, so this one's going to be neutral. All right? And this one, still positive, and this one, neutral, right? Okay? Then at pH 3, you know this molecule is going to get a net positive charge, right? Okay, now, when you go from pH 3 to pH 7, this particular proton or this particular group is not going to feel the effect of your pH adding and minusing, okay? Because before you start touching this guy, you still have this guy and this guy, okay? You still have those two, right? So the pKa's that are further away from when you have a condition that is neutral, that make the molecule neutral, charge equal to 0, okay? They don't really feel it, okay? That's sort of the message I'm trying to get across, okay? So when you want to calculate PI, right, you will probably look for a pH that is going to make your molecule equal 0 charge. And then you look at the pKa above it and the pKa below it. Those pKa's are going to determine, most importantly, okay, they're going to affect the pI the most, right? Because those are the ones that are going to change the most, right? Because they're really close to the condition in which you make this molecule neutral, right? Okay? So then what that means is that in this example, it's going to be between the 9.7 and the 4.2. That determines the pI of this molecule. Okay? Another example. Let's look at this particular example, and I forgot to write down here. This thing is histidine, so it has 5 groups instead of 4. Okay. That's wonderful, right? So again, you still have the 9.7, the 4.2, the 10, and 2.2. And now I have another one that's 6. Okay? All right. Let's do this again. Let's say when the pH is equal to 7, okay? This one, pronated, depronated. Pronated, yes, okay? So it's going to be a positive charge. This one, negative charge. This guy, positive charge. Oops, positive charge. This guy, the pKa of this one, histidine, when it's charged, which one gets charged? Which atom gets charged? This one, right? Now, in biochemistry, you rarely see like N minus. So this pK is actually referring to this, okay? It's actually referring to this. All right, so if the pH is above the pKa, it means that the proton here is going to get pronated or depronated. Depronated, yes, okay? So when it gets depronated, then the thing is neutral, okay? It's neutral, right? Makes sense, okay. And then you have minus. Okay, so we again identified a condition in which the peptide here is going to look neutral, right? 2 positive, 2 minus, 1 neutral, okay? Now, if I want to calculate pI for this thing, I'm going to say the pKa right above 7 and right below 7, okay? Above 7, I'm going to pick who? I'm going to pick 9.7. Right below 7, I'm going to pick 6, okay? And then divide by 2, right? That is going to be the pI for this particular molecule, okay? So you always try to first find a condition in which, right, just say find a pH in which the molecule becomes neutral, okay, just by assigning positive, neutral, minus, okay? And then you take the pKa above this pH and below this pH, divide by 2. That will give you a very good estimate of the pI for this protein, okay, or peptide, right? Now, of course, you can't do this when the protein is like 300 amino acids long, okay? I'm not going to have you in an exam count how many ionizable groups you have in a 300 amino acid residue protein. Okay? That's just nasty. Okay, I won't do that. Okay? And it turns out there's a lot of websites out there that simulate PIs, okay, for you, and they're gonna calculate based on different algorithm and then give you an average of what they think, what the computer thinks the PI is going to be. Okay? Now, all of this calculation, you only use them as an estimate. Okay? It's never really the true PI unless you do an experiment to determine it. Okay? Why is that? Okay? Because even though here I say, oh, okay, pK is 4.2, but this 4.2 I actually got from the free glutamate. Okay? In reality, when you have a protein, okay, that's 300 residues or 400 residues, it's really big. Okay? So all of the surroundings, okay, when protein's full, you might have another positive charge right next to this positive charge, and then that's going to lower the pKa. Does that make sense? Okay? Because protein has 3D structure, right? Because of that, the environment in which all of these pKa's, okay, may or may not be very easy to guess. Okay, so in reality, the PI we only determine through experiment. Okay, but of course we can do an estimate. So that's what this website is for you. You can actually go on this website and then throw a random protein sequence to it, and then it's going to tell you the PI. Okay, and the PI it's usually pretty close. It's not going to calculate, say, 6, and then you do the experiment and it gives you like 9. No. It's going to be like 6 versus 6.2, 6 versus 6.1, right? It's pretty close. But just I want you guys to understand that in reality, if you want to determine a PI for a protein, you have to run an experiment. Okay? Does that make sense? We're cool? Right? And why is that? Because sometimes it may not be easy to predict what the pKa's for each individual ionizable groups. Okay? Because you have 3D structures, and it's going to affect the pKa differently between different protein structure. So it's not an easy thing to predict. Okay? But of course, with the advance in bioinformatics, we're getting better and better. Right? But still, at this stage, we can try to predict, but there's still an error margin. Cool? We're cool with that? All right. So why is PI important? It's actually important for a couple of things. Today I won't have enough time to go over electrophoresis, but PI is important. Number one, solubility of the protein. Okay, so every protein is going to have a PI. Okay, we just agreed. Every protein has its own PI, right? Depending on whether or not it has more acidic groups or more basic group. Okay, now. So basically, if you take a look at these pictures, okay, at high pH, protein is usually soluble. Why is that? Because your protein is heavily charged. Okay, your protein has a lot of charge, and when it has a lot of charge, the water, okay, it's going to form hydration shells. Okay, you're going to have sodium ions and other small metal ions interacting with your protein, and it's going to be quite soluble. Okay, so you guys know that everything that's charged is soluble. Okay, at low pH, same thing. Okay, when it's low pH, the protein becomes positively charged. So then you got the Cl minus; those guys are going to come near it. Okay, and then interacting with your protein, hydration shell happens, and then your protein is soluble. Great. Okay, turns out, at the isoelectric point, your proteins are going to aggregate. Okay? You actually have proteins come really close to each other. Okay? Why? Because your protein becomes net neutral in charge. So you have reduced amount of electrostatic interaction between the protein and the medium, because the protein itself is already neutral. Okay? As a result, the proteins are going to have other forms of interaction with itself, okay? And they're going to start to get really comfortable with each other, and they're going to precipitate, okay? So if you look at a graph where you have the pH versus the solubility of a particular protein, this example is beta-lactoglobulin, but every protein has a graph that looks like this, okay? And what you can see is that solubility drops to a minimum at which the pH is equal to the PI. Okay? So why is this important to you guys? Okay? Most of you guys are biotech majors. Okay? Why is this important? What do you think? Anybody want to take a guess? Why is this important to you? Let's say you want to do an enzyme reaction. Okay? Enzymatic reaction. All enzymatic reactions, we include buffer, right? Your medium is a buffer, okay? You can choose what pH you want the buffer to be at, right? You probably want to stay away from the PI, okay? Because at PI, your protein solubility is lowered, okay? So then that means that your reaction, you cannot increase more protein and make it faster because there's an upper limit in which your protein is soluble, okay? Because usually when we do an enzyme reaction, right, enzymes are catalysts, so the more enzyme I put in it, the faster the reaction, right? So you want, let's say you want a super fast reaction, right? You want as much enzyme in the solution as possible, okay? So then, in that case, you don't want to do your reaction at the PI because you're going to lower the solubility of your protein, okay? So that's important, right? So that's something that you should consider when you're designing an enzyme assay that is going to be, looking at the activity of your enzyme. You want to stay away from the PI, okay? And now you're going to be like, oh, okay, so, why don't I just jack up the pH to like 14? Well, your protein dies at 14, okay? At extreme pHs, your protein die. At PI, your protein aggregate, okay? And you're just like, okay, that sucks, okay? So it's a lot of times up to experience and up to your experiments to determine at which optimum pH you should use for your enzyme assay, okay? Your enzymatic reaction. All right, cool. So this lecture, I want you guys to be comfortable with calculating PI, okay? Both for a amino acid that has 2 ionizable groups and for a peptide or anything that has polyprotic characteristics, okay? Multiple pKa's, how to calculate PI in those cases. Cool? We're good? All right, so that's it for today.